Okay, welcome to video 1.1. This video is going to cover a subsection of chapter 1 in your textbook. We're going to cover topics of units, SI units in particular, scientific notation, and units that aren't based on SI units but are actually derived. That'll include introducing you to this really powerful technique called dimensional analysis. Most of what I'm going to talk about in the next 10 minutes is something you probably have seen in a previous chemistry or physics course, so we'll move through it pretty quickly just to get you refamiliarized with the language that chemists and physicists and scientists use. So virtually all of science is based on the scientific method, as all of you know. So typically we generate or think of a question, a scientific question. We design a particular set of experiments to test or evaluate that question, and then we do some measurements. And really all of science is based on measurement. So we get some numerical answer, some number. But that number really is meaningless to us unless we can provide some sort of context for what it means. And so that context in science is what we call a unit. And there are a few different basic systems of units. There's the US custom system. So if you grew up in the US, you're familiar with units of measure like the inch or the yard or the pound. Scientists don't use that. We're not going to use it in this class. We're not going to use it virtually any time in the STEM discipline at Colorado College. What we will use, though, is this sort of agreed upon basis set of units called the SI unit. The SI unit means that all physical quantities can be broken down into really these basic values. And so this table 1 represents all of the different SI units of measure. So if you have mass, we measure that in kilogram with the corresponding abbreviation. Length, temperature, amount of a substance, notice that's the mole. We'll talk a lot about that in this class. Time, electric current, luminous intensity. This is the basis of all measurement units, of all the context of measuring in chemistry, in physics, in engineering, in all of it. As you all probably know, there are a whole bunch of different physical quantities on this planet that we can measure that don't fall within any of these 7 categories. Those will be what we call derived units. So quantities based on some mathematical relationship that can derive a new unit based on these base set of individual units. In this class, we won't really talk about electric current at all or luminous intensity. And so the vast majority of this class will deal with quantities of mass, length, temperature, amount, and time. That's not to say that these won't be used in other chemistry classes. They certainly will, but for Chem 107, we'll be relegated mostly to these 5. When we're representing numerical measurements in the sciences, often we're dealing with really large or really small numbers that can be cumbersome to represent. So if we look at this example here, this is example A, this number 0.00000000372 meters, this is using the base SI unit for length. This represents the diameter of a sodium atom, so really small object. This is cumbersome to write, right? We don't typically as scientists represent this. In case, what we do is use this type of notation that we call scientific notation. So scientific notation is really just a simplified version of the same number. It's exactly the same quantity, but we're going to represent it using exponents, this component here. You probably all remember this, but I'll give you a quick refresher. So if we want to represent this diameter in meters using scientific notation, what we do is we take that decimal and we move it all the way over until it's 1 unit past the first digit in this number, and then we count how many numerals we actually shifted it, and that's going to correspond to the exponent here. If we shift it right, which we do in this case, that means it's a really small number because it's several zeros after the decimal. That's going to be a negative quantity. If we shift it left, is the case with letter B here, that's going to equate to a positive exponential quantity. So in this case, if we count every numeral we move over, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're moving to the right, so this value becomes 3.72 times 10 to the minus 10. This letter B represents the diameter of the Earth, so this is a very large quantity, same unit, meter in this case. In this case you can see the decimals here. We can count 3, 6, 9, 10, 11. That puts the decimal right there. That gives us a value of 1.5 times 10 to the positive 11. Okay, let's do a couple quick additional examples. So let's look at this value of 55,000 here. You can see the decimal here can be written explicitly. It doesn't have to be, but in this case it is. So we move it over until we have just one numeral to the left of the decimal. That's going to give us 5.5 times 10 to the fourth, 4 decimals that we moved over. Do the same here in the opposite direction, so 1, 2, 3 gives us 3.20 times 10 to the minus 3. Notice that I kept this 0 in both because that 0 is important. We'll talk a little bit more about that when we get to significant digits here in a second. Okay, an alternative way to represent numbers instead of scientific notation, or actually in addition to, sometimes we can combine these, is to use prefixes, which are really just text representations of the exponent that we typically use in scientific notation. If you all use this before, if you've ever used a unit of centimeters or millimeters or gigabytes or megabytes or kilobytes, what you're doing is using a text-based prefix to represent some large or small number. It's just a convenience way. So this table 1.2 represents all of the general prefixes that we use in replacement of scientific notation. So you can think about this as really just a conversion table that allows us to use this factor here to convert across several different units. And this sort of blank space right in the middle where I have this green arrow, this is where you'd insert whatever the base SI unit is that you're converting between. So this could be a gram or a meter or any one of those 7 units that we talked about several minutes ago. So for example, let's pretend that we have a measurement of, say, 1.5 meters, and we want to convert this to, let's say, millimeters. We could use this table to help us do that. But before we do that, I want to introduce this idea which will be a really systematic way to help us convert units, and it's going to be the basis of much of this class, honestly. And that's called dimensional analysis. And so dimensional analysis, I have the definition written here, is really a systematic way to convert between units. And so it is, without fail, the process by which we can do more complicated math, but never mess up what our final unit is. And the simplest use of dimensional analysis is just converting between different units like this. And so in dimensional analysis, I'll show you how you would set up this process. We'd start with the value that we want to convert from. In this case, we have 1.5 meters. We're going to draw a vertical line right after that value. That vertical line is going to represent multiplication operation, and then we're going to write a horizontal line that's going to represent division. And so what I'm going to do next, so I have my original value of 1.5 meters, and now I need in this space some unit conversion factor, which I can borrow from this table. So in this case, this table is telling me that 1 millimeter here, or 1 milli of any base SI unit, could be a millimeter, or it could be a milligram, or a millibyte. That's 0.001 of whatever that base unit is. That's our conversion factor right there, which we need to put into our dimensional analysis. So we'll put then on the bottom here, we'll put the same unit that we're trying to convert from, because that will cancel those units. So we'll say 0.001 meters is equal to 1 millimeter based on this conversion factor. And what I can do now is keep track of my units. So I'm going to come in here with this different color pen, and I'm going to say, because I'm dividing these two units, those two are going to cancel each other out, which means after I run this computation, the resulting value is going to be in whatever units are left over after this dimensional analysis. In this case, the only unit that exists is this millimeter. So I'm going to take 1.5, and then I have the vertical line, which means multiply by 1. So that's 1.5 times 1 divided by 0.001, and that's going to give me this value of 1,500 millimeters. Okay, let's do one more quick example. So we've got this value of 0.0056 grams. Let's pretend that we want to convert this to micrograms. So we go back to our conversion table here. We find where the micro is. So let's just highlight that. That's right there. So our gram would start here again at the base SI unit, and we're moving towards smaller directions, towards the micro side of things. So we can see our unit conversion factor is going to be this. That's what we're going to use in our dimensional analysis. So let's set up a dimensional analysis table again. So let's go over here. We'll start with the value we know, which is 0.0056 grams. Multiply by whatever our conversion factor is, which is going to go in these next boxes. And our conversion factor is always going to have the unit we're starting with in the denominator, which is going to allow us to get rid of or cancel that unit and convert it to the new unit. And so in this case, our conversion factor is right here. This is 10 to the minus 6, which is what micro means. That's what this sort of Greek letter mu means, represented right there. So that gives us 0.1, 2, 3, 4, 5, and 6. That gives us that many grams for every one singular microgram. Again, I'll go back to my green pen and I will just keep track of my units. This is the benefit of dimensional analysis. That gets rid of grams. So once I multiply this and divide this, I'm going to be left with simply the units of micrograms. So multiplying 0.0056 times 1 divided by this quantity is going to give me 5,600 micrograms, or I could write this in scientific notation as 5.600 times 10 to the third micrograms. Either way would be correct. There is basis for writing it one way versus the other, and we'll talk about that in a few seconds when we talk about significant. So we've talked about base units, we've talked about representing large and small numbers with scientific notation, but also with prefix notation. But what about all of the other physical quantities that we can measure as scientists that can't be represented by one of those simple 7 base SI units? So some examples that I have here are things like volume, which would be represented by this cube. We all know, hopefully, from sort of high school geometry, the equation for the computation of the volume of, say, a cube would be the length of this cube. Let's do that in red. So the length of this cube, we'll call this the length dimension. This is the width dimension, and we'll say that this is the height dimension. So multiplying these 3 dimensions by each other, each with their own unit of measure, in this case meters, would allow us to derive a new unit for volume. And so volume, as we know, is length times width times height. Each one of those is going to be in units of meters. So meters times meters times meters is going to give us a derived unit for volume of meters cubed. We could do the same thing for, let's say, area. So area is a little simpler. We know that as length times width. Each of those dimensions are measured in meters, so that would be meters times meters, which would give us units of meters squared. These would be derived units. What about if I have, say, this volume in meters cubed, but I want to convert this to, say, a volume in centimeters cubed? Well, I could do that with the trusty old dimensional analysis. So let's do this really quickly. Let's take a value of, let's say, 1 meter cubed, and let's set this up dimensionally. So again, we're starting with the value that we know, which is 1 meter cubed, and we're trying to get to this centimeter cube value. Okay, so we need some sort of unit conversion. That's what's going to go here with meters on the bottom. And so we remember from the table before that there are 100 centimeters in 1 meter. So I could write this up. We'll do this in a different color. So for every 1 meter, we have 100 centimeters. But notice that here I have meters cubed, but now I'm only dividing by meters, which implicitly is meters to the first and centimeters to the first. So this would only cancel one of these meters, not all 3 cubic meters. So in that case, what I'd need to actually do would be to run this conversion 3 times, where I then say, let's say we cancel this, so we'll do this in blue. I get rid of this meter, but I only get rid of one of those, so this becomes meters squared. Now I need to run this a second time, which is 1 meter for every 100 centimeters. Okay, same thing. This meter is going to cancel one of these. Now I'm going to be left with just meters. So I'm not quite to centimeters yet. I need to run this one last time, which makes sense. I had 3 meters, so I need to do this conversion 3 times. So 100 centimeters per 1 meter again. And let's grab that meter. That's going to cancel this meter. So now if we look dimensionally, we have no meters left in all of our dimensional analysis. Instead, we have a centimeter times a centimeter times a centimeter, which is the same as the centimeter cube that we're trying to get to. So if we compute this, this is going to be 100 times 100 times 100, which is going to be 1 with 1, 2, 3, 4, 5, 6 different zeros in units of centimeters cubed. So all other physical quantities, whether they're chemical or physical or biological, that have a numerical value associated with them, so some measurement that isn't one of the 7 base SI units that we introduced right at the beginning of this video, those are all derived quantities. So table 1.3 here just represents a handful of some very common derived densities or quantities. We just talked about area and volume. Some other common ones that we'll use a lot in this class are density of an object. So density is the mass, how much it weighs per volume. So that's going to be in units of mass, kilograms per volume, cubic meters. So these are derived units. Speed, so velocity is distance per unit time, acceleration, force, pressure, energy. All of these things are simple units that are derived from whatever the mathematical expression is for each one of these related quantities. So let's do a quick example then. So let's scroll up here. Let's do this example that I've got written out. So the density of a gold bar is 19.31 grams per cubic centimeter. So that's our derived unit there. So grams per cubic centimeter. And what we want to know is the volume of the gold bar that has a mass of 12.4 kilograms. Okay, so we need to use dimensional analysis again, and we need to sort of think backwards. So we've got this thing that has a mass. So we've got a mass of 12.4 kilograms, and what we want to get to is a volume, and that volume is going to have units here of cubic centimeters, but we don't know what that is. And so we need to figure out how to go between these two quantities, mass and volume. And the conversion factor here is going to be this thing that has a derived unit that includes both of these quantities. So we've got some mass per volume, right? So mass and volume. This is our conversion factor. Okay, so let's do this dimensionally, and let's just start with the known quantity that we have. So let's do 12.4 kilograms, and just as always, we're going to set it up in our dimensional table like this. We have this conversion factor here, but note that the units of this derived unit of this conversion factor is in grams per cubic centimeter, not in kilograms, which means we're going to have to do one additional step before we can use this density conversion factor, which is to convert kilograms to grams so that we can employ this conversion factor. And so if we go back to the previous table that represented our prefixes, we know that for every 1 kilogram or kilo of any SI unit, that's going to equate to 1,000 of that SI unit, in this case grams. So we'll go and keep track of our units. So I'm going to cross these out. So now we're in units of grams, which is good because our conversion factor also employs units of grams. So we can now use our conversion factor. We'll add another vertical line, which indicates multiplication. And to keep our units canceling, we'll take this 19.31 gram per 1 cubic centimeter. And the reason I put it as 19.31 on the bottom was because I wanted these grams to cancel, and that was the only way to do that. So those grams go away. Now I'm in units of cubic centimeters, which is exactly what I need for this. So let's do the math really quick. So this is going to give us a value of 642.15 cubic centimeters, and we know that we have this in units of cubic centimeters because we used dimensional analysis to keep track of every unit. So we canceled all of these other units. The only thing that we have left in our dimensional analysis is this cubic centimeter, and this is our final answer.